In this recording, we'll talk about the theory of island biogeography. This is one of the foundational ideas in all of conservation biology. It is one of the most important ideas in all of community ecology. And it is really vital for understanding how habitat patches get the species that they do. So this theory was derived by Robert MacArthur, whose name you've heard before in terms of competition between warbler species, and E.O. Wilson, who's by all accounts the greatest naturalist of the 20th century. He's also called the Ant-Man. But we'll look at some of the data that caused them to put the idea together in terms of species diversity on islands and in patches compared to large contiguous areas of habitat such as continents. We'll look then at the rates of colonization and the rates of extinction that we can expect to see in islands and patches that behave like islands. We'll look at the differences in dynamics in large and small islands and near versus distant islands, and put them together into a comprehensive accounting of what we can expect for species diversity on islands and in habitats that behave like islands. Then we'll look at a test of these ideas of large versus small and near versus near versus far. And finally, we'll finish up with applications to conservation biology. So first off, species diversity in islands and habitat islands. So any patch that is isolated from similar patches by unfavorable habitat can be modeled as a habitat island. The ideas that we're going to talk about come from islands in the ocean, but what is an island in the ocean? It's just land surrounded by not land, and any species that's adapted to land is very unlikely to find it possible to survive in water that surrounds the island. In the same way, forest patches in a large expanse of prairie would behave as islands, and little isolated grassy glades on a mountaintop in the middle of a gigantic expanse of forest, that would also behave as an island. So these ideas are not limited to oceanic islands. They are applicable to any habitat patch that is surrounded by inhospitable habitat that is different. So you can say pretty much on first principles that the ability of a species to colonize one of these islands would depend on the distance it is away from some source of species. So if you're close to a source of species, and let's just say they're traveling randomly in all directions, if you're close, the likelihood is high that a species will eventually find you and colonize you. On the other hand, if you're far away, the likelihood is much, much smaller than in a near island, simply because the distance involved means that if individuals are dispersing randomly in all directions, the further you are away, the fewer individuals are going to go precisely in your direction. And the longer it will take for them to get there, so the fewer of them will survive. Now, the area of the island determines the size of the population that can inhabit it. And that is directly related, as we already know, to the risk of extinction. So large islands should support larger populations of each species on them, and that means that they should have a lower risk of extinction. And so over the long term, larger islands should have more species than small islands. So colonization affects the number of species on an island, because the closer an island is, the more species are likely to get to it. But the size of the island affects the extinction rate of those species. The larger the island, the larger the population, the lower the extinction rate, and that means more species will persist for longer on large than on small islands. So that's the general rationale. Now, what are the sources of these ideas? Well, here is a graph derived from the Southwest Pacific, looking at islands near New Guinea that support different numbers of bird species. So on the x-axis you see the area, and on the y-axis you see the number of bird species. And the color coding has to do with how far away from the island of New Guinea they are. Now, New Guinea is an enormous island. It is huge. It is one of the most biodiverse places on the face of the earth, and in particular, it has hundreds and hundreds and hundreds of bird species. So, some of these hundreds of bird species are likely to disperse randomly and find these islands. Now, let's investigate this pattern closely. Notice that the islands that are far away have a very steep relationship between area and number of species, right? Okay, and that is because the larger islands can maintain larger populations that have a relatively low risk of extinction. The small islands cannot do that. They have a high risk of extinction, so many of the species that arrive on these small islands will go extinct. And many of the species that arrive on the larger islands will stay and persist and not go extinct. So this very steep slope here is due partly to the difference in extinction rate, which is quite high. But why is the slope so much higher than for intermediate or near islands? Well, it has to do with the fact that once a species goes extinct on one of these small islands, the probability that another species will recolonize, or that that species will be rescued from extinction by a new individual of that species, is very, very small. So, small islands that are far away have high extinction rates and low colonization rates. Far islands that are large have small colonization rates and small extinction rates, so they maintain more species. The intermediate islands are uniformly higher in the number of bird species they support, and that is because they are easier to colonize. So yeah, the area is the same here and here. Why is this higher? Because they're closer. They're closer to the mainland, they're easier to colonize. But notice that you have the same negative relationship. So you get higher extinction rates in the small islands. The reason they're not as high is because you get recolonization more frequently. Finally, the really near islands basically are getting colonists constantly. And it doesn't matter what the extinction rate is, because they're getting so many colonists that extinctions are basically invisible. As soon as a species goes extinct or is threatened with extinction, more individuals arrive from the mainland and maintain the same number of species. So the ability to get to these islands depends on your dispersal ability. And you can ask how these patterns change when you have near islands and far islands, and you have species that have a differing ability to get to these islands. So first let's look at birds. Okay, so birds can fly. They find it very easy to disperse. So the Azores are a string of islands that are quite far from the African mainland. They have relatively low number of birds. The Channel Islands are relatively close to their mainland, off the coast of Europe, and that is the reason that the Channel Islands support more species for a given area is because of the higher colonization rate. Birds colonize more easily. On the other hand, ferns don't have that ability. Ferns can't disperse well, regardless of how far an island is. So the Channel Islands and Azores fall into the same regression line here. They line up exactly according to their area. And that's because the main thing that regulates the diversity of ferns is their ability to survive on islands once they get there. They don't get to islands very often, however. So it makes a difference here when you have somebody that can disperse well versus an organism that can't disperse well. Here, colonization plays very little role because salt water is salt water, but area plays a big role because the larger the area, the lower the extinction rate. Here, both area and distance make a difference because birds can cover this short distance much more effectively than the long distance. Not true of ferns. They are limited regardless of how far out there that island is. So let's revisit the idea that extinction risk is related to population size. And here's a graph that you've seen before in a different figure when we talked about stochastic extinction back in when we're talking about population dynamics. And this is the risk of extinction, percent number of extinctions based on population size for islands of different sizes in islands off the coast of California. And you see it dramatically affects the extinction risk. So size matters and distance matters for most species. So when we put these ideas together, we get a relationship that looks something like this. Now, people consistently misunderstand what these curves are and how we get them, so I'm going to take some time to go through them. But on the y-axis is the rate of colonization or extinction. So the rate of colonization declines as the number of species on the island increases. Why? It's because colonization must involve a new species that is not already on the island. So when you have no species on the island, every arrival is a new species. On the other hand, if you have 100 species available to colonize an island, and all 100 have colonized the island, then it doesn't matter how many birds fly out to the island, they are all already there, and the number of new species arriving is 0, because the species on the island are now the same as the species in the source population on the mainland. Here is the extinction rate, and the extinction rate increases with the number of species on the island. Well, duh, the extinction rate has to be 0 when there aren't any species on the island, but why does it increase this way? It's because more species have to share the resources available on the island. They maintain smaller population sizes. So this curve for extinction goes up. Where the lines cross, you have an equal rate of arrival of new species and an equal rate of extinction of species on the island. So the number of species that you find on the island is going to be somewhere right around this equilibrium, because as fast as they arrive, some of them will be lost to extinction, and they balance each other out. If the arrival rate is 0.1 and the extinction rate on the island is 0.1, then they exactly equal, and the number of species neither grows nor declines. How many times have we heard that phrasing in ecology? Now I'm going to go through the logic behind these curves because people mess them up pretty consistently. So first, let's look at the colonization curve, and let's ask why it decreases. Let's be sure that everybody understands this. So we're going to have 6 species available to colonize an island, and we're going to roll a die to see which species gets there. Okay, so we're going to start out with 0 species on the island. Okay, and it's going to be a random process. And this is how we imagine island biogeography processes. Colonization is a random process. So on the y-axis here, we're going to have the rate of arrival of new species. That's what the colonization curve is. It is not the arrival of individuals. It is not the number of species on the island. It is the rate at which new species arrive on the island. Okay, we have 6 possible species that could colonize this island. Now, if we have no species on the island, then every new arrival would be a new species. So here we have an empty island and we have our first individual arriving, and by definition, it's a new arrival because all 6 of these species would be new to the island. None of them are present when there are no species on the island. So this is a new arrival, and the rate at which new species are arriving when there's 0 species on the island is 1. Now, once you have 1 species on the island, what is the rate of arrival of new species? Well, only 5 of the 6 species are now new arrivals. You can get a whole bunch of individuals of species 1 arriving on the island, but it's already there. So that's not a new arrival. Only 5 out of 6, or 0.833, would be new arrivals. So the probability of a new species arriving is less now than 1. It is 0.833 because only 5 out of 6 are new species. If you get 2 species on the island, then fully 2/3 of the species available would be new arrivals, and 1/3 would already have been there, and they don't count as new arrivals. See how we're going here? So, when all 6 species are on the island, the rate of new arrivals would be 0, because any individuals that fly out from the island, from the mainland to the island, belong to species that are already there. There are no new species coming once you have 6 species on the island. So these are all the species available. They're already on the island. It is not possible to get a new arrival. So the colonization curve must decrease with the number of species on the island. Let's turn it around and ask why the rate of extinction increases with the number of species on the island. So when no species occupy the island, the extinction rate is 0. It has to be because there's nobody there to go extinct, right? When you get 1 species on the island, look, it's got the island all to itself. It has all the resources. It can have a really large population. Okay, let's think just very simplistically about each species dividing up the resources on the island evenly. So if we were to get a second species arriving, what would happen to the population of each? It'd be cut in half. Well, that means that the species has a smaller population and a higher probability of extinction. Remember, the probability of stochastic extinction is deaths divided by births, or death rate divided by birth rate, raised to the power of the population size. So we just cut the exponent in half, and we have a higher extinction rate. With 3 species on the island, you're dividing it in thirds in our imaginary scenario, and the exponent is even smaller, so you have a higher extinction probability. If you have 4 species, you divide it in fourths. Now the extinction probability is much, much higher, and so on if you get 6. So the probability of extinction steadily increases with the number of species on an island. Now, we've seen this relationship in many, many, many examples, and it holds really well. So we have high confidence that what we're seeing in this little conceptual model actually describes the real world. So how do we put them together? Remember, this is our basic scenario here. The rates of colonization and extinction balance at some point, and that gives you the equilibrium number of species on the island. If you get more extinctions, then some of the new colonizations will represent new species and they'll restore the equilibrium. If you get too many colonizations, the rate of extinction will go up and you'll restore that equilibrium. Now, let's address the issue of near versus far and large versus small and see which of these curves those things affect. First, small versus large. A smaller island has a higher extinction rate. There you go. So for any given number of species, a small island will have a higher extinction rate than a large one. That means that if you have the same colonization curve, if they are at equal distances from the mainland, so let's say that they're both 10 miles offshore, but one is large and one is small, there will be fewer individuals on the small island, or fewer species on the small island, because the extinction rate on the small island is higher. And that means that the intersection of the extinction curve and colonization curve is going to be here, yielding a smaller equilibrium number of species than on the large island, where the equilibrium is found here. So, island size affects extinction rate. Excuse me. Island distance affects colonization rate. So let's imagine two islands that are identical in size, but one is close and one is far away. Okay, so the extinction rate on those two islands is going to be identical because they're identical in size. But look, the far island gets much lower rates of species arriving because it's far away. The near island gets much larger rates of colonization because it's close. So if you look at where the lines intersect, the near island will have more species than the far island because the colonization rate differs. So distance affects colonization rate. Size affects extinction rate. So we can throw a bunch of curves together to represent different islands that have different characteristics. And here's a little imaginary kind of mishmash of far islands versus near islands and large islands versus small islands. And you can see the extinction rates go up as island size decreases. The thing to remember is that the high extinction rates are on small islands. The low extinction rates are on large islands. People always mess that up. The colonization rate is always low on far islands and high on near islands. People tend to remember that a little better. But you can see that you get a whole range of possible solutions here. And you got some large and near islands that have lots of species. You got some small and faraway islands that have few. And then you have islands that have different mixtures of characteristics that are somewhere in between. So not to get too complicated here. So this sounds really good. How can you possibly test this? Well, Dan Simberloff, who is still teaching at Florida State, tested this idea for his doctoral thesis. And what he did, which is a great story, he went to the Florida Keys. And of course, we think of the Keys as Key West and Key Largo, all these big islands. No, the Florida Keys are mostly these tiny, tiny little islets that might be only a couple of square meters in size. So Dan Simberloff got permission to drape several of these small islands with plastic. And he sampled the insects on these islands, draped them in plastic, and then fumigated them to kill all the insects. And then he asked, how long does it take for insects to come back to these islands? And do we see the same numbers of species on near and large, near and distant, near and large, near and small, far and large, and far and small islands? Well, so I'm only going to show you three because these are the clearest results. And here you go. So here's the pre-fumigation numbers of insect species on the near island. And here's the trajectory of recovery. And look, it's quite close actually. Here's an intermediate island. And here is a far island. And look, these are really close. This is not quite there, and that might be because we need more time to elapse before we get back to this level, but they are clearly going back to the pre-fumigation species numbers. So species richness recovers to very similar levels, and that is predicted by the characteristics of the island. Now, the interesting thing is that the species that you find there are not necessarily the same species as before the fumigation. So species number is conserved, but species identity is not. Okay, species identity can change, and what that suggests is that first come, first serve, and maybe a species that arrives on an island might block another species that could otherwise go there. But this is one of the great field experiments in the history of ecology. You can't do this kind of thing anymore because the National Park Service has taken over the Florida Keys, and they would not allow you to do this anymore. But Dan Simberloff got in before the rules got strict and was able to do this really elegant test of the theory. Not going to do island size here, even though he tried to test that as well. So we've got this cool theory, and it seems to really work. What do we use it for? Well, there are lots of habitats that can be modeled as habitat islands. Here is the state of Nevada in the yellow outline, and look at all these little corrugations here in this map. Those are mountain ranges, and they are surrounded by desert. So they are sky islands in a sea of desert. And you would expect then the larger sky islands to have more species than the smaller ones. You'd expect the sky islands that are near to the Sierra Nevadas here, which is the source of the mammals on the top of these islands, to have more species than the ones that are far away. And in fact, that's exactly what you see. Here's what a sky island looks like. This is Great Basin National Park, actually, in the middle of Nevada. And it's surrounded by this really hot, low desert. Clearly, alpine species here find it difficult to get from one mountaintop to another. And here's the payoff. Here's the area of those sky island mountain ranges, and here's the number of mammal species. Look at that. Perfect. It's a perfect predictor. Here's how isolated those ranges are from either the Rocky Mountains or the Sierra Nevada in California. And once again, it's a perfect predictor. The ones that are very close have many species. The ones that are very isolated have very few. So species richness follows very precisely the predictions of equilibrium models of island biogeography.